Mr. Mueller. Thank you very much.
For your introduction. Yeah, good morning, everybody. Now Adam just warmed us up, and now we go to this very cold topic. Actually, this 100-year journey is not my invention. Actually, that was last year created by the UNESCO. They just declared this year as the 100th year of quantum computing. I don't know exactly what's behind, but actually it kept me reflecting a little bit on these things and what the journey was and how it will continue. And that's actually a quite interesting thing. What I also did, I have almost no physics in this talk, so no Hamiltonians. The only what you may see is a bracket writing. I tried to look at this from an electronics point of view, from the classical side, but I tried to show also a little bit what we can see. Does it work? Yeah, it works. So you see, I will first go on these historics a little bit, and I also try to keep it as quantum mechanics because it's just more intuitive if you think and talk about quantum mechanics. It's really the pendulum, what you have there. And then we go just to a few of these topics and we'll end up with how it may continue. On the right, I just went to the lab because we are building up a new of these systems there, and I thought I will just make a picture of it. There is even the processor is not in, it would be here. But this is a cryostat, one which goes to these very low temperatures. That means on this plate here, look, here you have around 10 millikelvin, and this you have to be aware of. You have several more of this buck. That is the wrong one. How does it go back? There are several more of these stages on top, and you come from top and you start first with 50 Kelvin, 3 Kelvin, some 800 millikelvin, 100 millikelvin, 10 millikelvin. Actually, the 3 Kelvin is what we naturally have as lowest temperature. That's what we see in deep space. And everything below what we are using for this technology is completely artificial. It doesn't exist anywhere, even not in the universe. And so it's a quite strange environment. And that is also the reason why we, at the physical end, we really do not know everything of this thing. We are also exploring. So, yeah, they actually say 200 years of quantum, but actually from my point, quantum started here with Max Planck when he defined the quanta, and it's already 25 years longer. And then it just took, they really had quite a race of results which just paved the ground. And people started to think in this mode, and that's something very interesting, that Lilienfeld, at that time, from these results, he actually wrote the patent about the FET transistor. But it was not possible to manufacture it for many, many years. And so in the 47, the nice bipolar transistor made it for many years. And later, the FET, as we know it today, came back. But all that actually created a first know-how about quantum applications, and that was the laser, which has already very deep know-how about this, but it's still a mass technology. They didn't treat a single quantum. And then the real start was the demonstration of the DC squid. Actually, almost nobody knows it. This was done by some people at Ford Research, the car maker. Two guys did it there. So you see, it's really a quite diverse journey what we had. And then in the 80s, when Feynman and Manin started to discuss about the universal quantum simulator, which is more a kind of an analog part, and David Deutsch actually saw that this could be defined as a Turing machine, then it really came up. What I have to say to Peter Shor, actually today he always gets cited about his factorization, but he did something much more important. He showed that this quantum Turing machine can be treated as a digital system. And he also showed that it is possible to get this correction over the uncertainties of quantum. He just took this factorization as an example, and now he's very famous for this. Next one. We know many technologies which potentially could be available for computing. Actually, the first two are spin qubit systems. I just took this because that's our major topic. That one here shows you just a transmon. And here we have actually ions and free atoms. Actually, today, if you are interested in accessing such machines, at least that one, a spin system at the University of Delft, of course the transmon in IBM, are available on internet, so you could access that from outside. And these machines, actually you can buy. So there is quite something around, and that's also today the state of the art. For the further discussions, I would like to focus or limit it actually to the transmon, because I think it's the system which is most close to us. It's an electronic built atom, and it's controlled by microwave. Actually, this is also something from this journey. Only the wireless technology, which with its measurement instruments, actually allowed us to start this technology. The physicists never would have been able to actually create the market of these test and measurement instruments, which we used then later to actually build our experiments. So this is also such an effect that just the technology actually got ready for doing such experiments. Then it's another thing with transmons. Transmons are a macroscopic technology. The only nanotechnology you have is actually what you see here. This is the Josephson junction. I also cited this paper because that's a good thing of material science. These guys actually showed how to bring coherence times up in the range of a millisecond. That's really bright thing. Now, to look at such a system, it's very busy, but yeah, let's start with this. Actually, a transmon qubit is here. It's nothing else than an LC resonator. And yeah, it's this pendulum. Now we have a problem because we want to build a qubit that needs two distinguished levels, energy levels. Since everybody knows a resonator just has harmonics, we need to make that non-harmonic. And that's the reason to get the Josephson junction in. So that means our energy level differences between the different levels are just non-equal, and that gives us the opportunity with a specific energy, which of course is an equivalent of our microwave wavelengths, to work just with two levels. And that's the whole trick of a transmon qubit. To get this, of course, we have to cool it down, but this is an effect that our microwave photon has from its energy. It has a kind of temperature equivalent. Now, this is really the quantum device here. Now we have to interface it, and that's done very often with a resonator. This resonator is really the classical thing. It's just a pendulum, and this pendulum actually is coupled with a capacity. So in the end, you can think about this system. You have two pendulums, one a harmonic, the resonator, one an anharmonic, the qubit, and between you have a spring, a very weak spring. So this anharmonic is able to influence. That means in microwave technology, it means just to mix its frequency up on what we have here in the resonator. Now a setup is pretty easy. You have some microwave generators. You feed them here in the resonator, and here you actually homodyne down convert, and you look for your mixed frequencies from the qubit. So for this experiment, which shows you here on this side, the transition from the blue, that's the cold, that's the quantum response, to the red, this is our classical response. The classical response of this resonator is just its resonance frequency. If we now lower the temperature, and because this is not easy with these dilution refrigerators, this group actually took a trick. They feed, just with white noise, they feed the heat into the system just by microwave photons. So that's basically what you finally see here. Here we are on about 100 millikelvin, and here we are in our nice, more or less room temperature world. If you go from room temperature now down with your heat, you can do following tricks. You actually just feed here the wavelength, which is needed by the qubit to switch its level. Resetting, you just wait. It can get lost. It just gets lost. But you feed your wave just in. You don't have to care. You do not need to be quantum, because if you want to switch your qubit from 0 to 1, you flood it just with your with your wave packets. If it's ones-on-one, you want to read it out, and now it starts. You actually start to feed photons to the resonator in its own resonance frequency, which is, of course, slightly different from the qubit. And then you get at the room temperature actually this peak. If you now lower your temperature and you have very, very low power here, then at certain time you will see here the modulation. And this is actually what we see here. Now, if we go so low with the temperature that just think at the semi-quantum scenario, where we feed here only piecewise wave packets in, and because of the cold environment, they stay for, let's say, microseconds here in. There is a lot of time for this wave packet actually to interact with the qubit and to get modulated. So in the end, at below 100 millikelvin, you just will see these two peaks, and actually that is now what the spring between the two pendulums is doing. If we have here a 1, then this pendulum is a little bit heavier, and through the spring it modulates our resonator frequency a little bit down. On the other side, if it's empty, then it modulates it up. And these two peaks, what we finally see here after demodulation, I have to say here for the external ones, what you see here after demodulation, actually you only see these two frequencies that are directly the 1 and the 0 you always see in the brackets. It's all, from that point, all very classical. So, looking at this famous Bloch sphere, which is sometimes good, sometimes not, the first peak is here, and the second peak is here. Everything else of this Bloch sphere is not directly visible to us outside of the quantum device. But it is possible to see these states between as a projection on this axis between 1 and 0. This has a consequence. It's only statistically possible to see it. And that's exactly the weak point. This means if you want to work like this, then you need to sample and you need to do statistics. So this is not really attractive to build a computer in the end if you have to run your algorithms thousands of times just to get out these statistics. And that was the big thing what Peter Shor did when he actually defined that if an output state is clear only in the basis of 1 and 0, then we will get fast. And that's a little bit the thing, what I always say as a user of quantum computing. It is not so important what happens there in the quantum state, because that is just like you use another application, or you are using some CMOSFETs in your computer. It's not so important that you really know these physical details. And I think that's a strong point for later quantum computing. Of course, then you can start to do gates, actually from an electronic point of view, that are just applying sine and cosine waves, microwave. it's a quite usual thing. You can do the Hadamard gate, which actually flips you your states in the equator. That creates you a perfect random generator. If you are curious about, just go once to one of these public computers and try it. And of course, with more qubits, you can do C-note swap. C-note is actually the XOR, what we know. And then if we have multi-qubits, then of course, all the superposition ends up in this huge state space, which then can be accessed in this so generalized or parallelized way, which is on one side a strong point of quantum computing. If you just want to change a single bit in a single state, it's a heavy thing, so that's perhaps not what a quantum computer want to do. Error correction, you may have seen this many times, but I just want to tell you that error correction, that can be done here with this. That are signs for this C-note. And C-note is just XOR. And what you see in this error correction, it's just correcting with 3 bits and majority voting. But since a qubit has 2 parameters, we have to do the error. We also need 2 kinds of error corrections. So we correct the state and we correct the phase. And that's a big deal, because error correction requires connectivity between qubits. That means couplers. And this is something where people really have to work at. That's today's, I think, weak point of almost all systems. To go a little bit more in the direction of applications, I do not really emphasize a lot of. I think we can divide them in about 4 different categories, what you see here. And I really have to mention here, let's put this also on, Stephen Jordan. He was working for the US NIST for quite some years, and he collected this quantum zoo. I think now he is with Google, but he still maintains the quantum zoo, and that's that's really that collection for algorithms where you find almost everything what's today in the field. That's really the library. So to get to a conclusion, as much as we can conclude, because the 100 years were not enough, and it will be still need a few more years to get to a real computer, at least also to a commercial available computer, because that's another journey. But what you saw 100 years ago, we got the road paved, and then advancements of devices created lasers, and the second, which then created the second generation and actually kicked off the whole thinking about quantum computing. What we see today, people are asking for these new applications, for new opportunities, and that will create actually applications in areas where people just have no other choice than using the new technology. And these applications actually, they will prepare the market, because these applications actually will demonstrate the reliability of the technology and also manufacturability. And that then will get us over this point where foundations or companies need to spend really the billions to build up a fab. That's really, in the end, the risk of when to do this is really a big thing. And from my experience over this long time in research, that if you once have your prototype, it takes 15 years. So, my hairs are too gray, but I will watch the scene. I thank you for listening, and that are actually the two groups I'm working in and the many PhD students. Thank you for listening, and
thank you very much
for questions.